Exercise 12. Consider a region S bounded by y equals e to the x. Whoop. And y equals x plus 2. Yep, there we go. So the sliver here, that's our region S, which is the base of a solid. Find the volume of the solid formed by square cross sections perpendicular to the y-axis. All right, so since our cross sections are going to go perpendicular to the y-axis, that is going to make a horizontal representative rectangle like this one. Okay, so imagine that we're going to turn these things into square cross sections. These squares are coming upwards here in a third dimension, like along a z-axis or something like that. It's basically going to trace out a square prism that will look sort of like this, where this rectangle down here at the bottom corresponds to this horizontal rectangular, this representative rectangle there. All right, so in order to find the volume that we're looking for the whole entire figure, we need to first find the volume of one of these little prisms. What's the volume of a prism? It's the area of the base multiplied times the height. And our base is our square cross section. And then our height here, of course, is going to be the width of this rectangle. So in order to find the area of the square, we need its side length. Right, let me zoom in on this little picture here. The side length of that square corresponds to this dotted red line, or red line segment that's right in there. And notice that this is a change in x. Project that down to the x-axis. And we are moving from left to right. That's a change in x. So instead of doing top minus bottom, we have to do a right minus our left. If we did top minus bottom, that makes a vertical representative rectangle. That gives us a totally different volume here. So that means, that indicates that we are going to have to solve both of the equations that they gave us for x. Not terribly difficult, but it is an added complication that the other problems just didn't have. All right, so let's go ahead and come over here to Notability so we can do some writing. So we said that we needed to find the side length, this side length, and we do that by solving each one of these things for x. Starting with y is equal to e to the x. I'll solve that thing by taking the natural log of both sides, right? Okay. And then we have the natural log of y should be equal to x. That corresponds to, say, this x coordinate right down here. Here, let me just go ahead and trace this thing down. Boop, 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 boop. That's the natural log of y. Okay, and then let's do the same thing with our line. And by the same thing, I mean not exactly the same thing, because we're not going to take the absolute value of it. I mean, absolute value? When did we ever do that? We're not going to take the natural log of it. It's just going to be subtracting 2. Y minus 2 is equal to x. And that would correspond to this x coordinate right here, y minus 2. So to find the length of this base segment, the side length of the square, we just subtract those two, just like we used to do with top minus bottom, but this time it's going to be the right side minus the left side, like this. If I can find my eraser, yep, there we go. So the natural log of y minus 2, that quantity, make sure you put some parentheses around that or distribute that negative sign through there, right? Okay, so since this is a square, its height should be identical to that. And then as we said, since the width of this thing is actually vertical, it's indicating a change in y, a delta y for the width of the rectangle, which makes a delta y for the height of our little prism. Okay, so the area, as we indicated, is just a side squared. For the area of that cross section, we integrate that thing with respect to y. We should be able to find our volume. So I think that we have enough information. I think, let's see. So we're going to take the definite integral from, what are our bounds of integration? Well, we don't have any numbers here. And they're obviously not on little grid marks, so how do I find those things? Looks like we're going to have to set these two equations equal to each other in an algebraic sense, x plus 2, and then, well, good luck solving that thing by hand. Looks like this thing is a calculator active kind of question. So we'll have to put this stuff into the calculator so that we can solve and find our points of integration. So our limits of integration right here. So if I were to put this in, like up until this point, we mostly just found our x coordinates. We actually want to find our y coordinates, right? Here, let me come back over here and draw some stuff on our picture to make this abundantly clear. Okay, so we don't want this x-coordinate down here because we're going to integrate from bottom to top, from, let's say, along the y-axis. Yeah, I need the eraser. So really, I need this y-coordinate that's down here. It's pretty close to 0. I'll call it A, and then I need this y-coordinate up here at the top, which is pretty close to the number 3, and I'll just call that one a B, which it doesn't even look like. There, that's a little bit better. So I'll find those things into the calculator. So go ahead and take a moment to plug both of these things into the calculator, y1 and a y2, so that we can find our points of intersection. And it should look sort of like, I don't know, here, let's say that this, and then let's do this. All right, so you can see that we have both of our equations in there. And then we will go to our zoom setting, choose maybe a number 4. That should be a big enough window for us to see a complete graph. Yep, that looks good. All right, so here's our region S. And to find those points of intersection, we'll go to second, trace, calculate menu, choose number 5 here for intersect. And you'll have to go through this whole questionnaire. First curve, it's the blue one. Yeah, and you can see it's the exponential one. Second curve, it's the red one. It's the line. Yeah, hit enter. Now we do have to guess because we have 2 points of intersection. It doesn't know which one that you want. So either move your cursor closer to it or type in the x value that it's pretty close to, and it's really close to -2, so I'll just type that in. It'll find it for you. You can see it's pretty close to x equals -2, but we don't care about the x coordinate. We only care about the y coordinate right there, and it is typed in as y down at the bottom. It is stored as y in the calculator currently, temporarily. So if I quit back to the home screen and type in alpha y, hit enter on it, you should see that number. But we want to store that as a. So here, I'll hit store alpha A. Did you see the store button? Okay, hit enter. Now it's A. Let's do that one more time so that we can find that upper limit of integration. So second, trace for the calculate menu, choose number 5. Okay, first curve, second curve questionnaire. And guess we do have to scroll over to the other one or hit, let's see, that looks like it's, I don't know, maybe about an x equals 1-ish. Boom. Yeah, it's pretty close. All right, so here is our next y coordinate. Oh, it's pretty close to pi. Just missed it by a little bit. And then now this basically stored on top of the previous y, which was why it was really important for us to store the previous one as an A. We're going to store this one as a B. So if I hit alpha y and store as an alpha B there. Yep, there you go. Hit enter. Now it's that number that's pretty close to pi. All right, so we're going to just build our definite integral right here on the home screen. Math, choose number 9, and then from A to B for our 2 limits of integration. Okay, and inside here, don't bother with your y1s from your alpha menu. Yeah, don't bother with these guys. We don't want that. Can I just get out of this menu like this? No, you can't. Of course not. Okay, so maybe I'll just, wait, maybe I just hit that again. Nope. Okay, I have to quit out of it. All right, whatever. So type it in like what we had on our paper, which was the natural log of y, natural log, which is, yep, there right there. And you can type in y if you want to, but look, I have to hit alpha in that button. It's much easier to just type in x. As long as we put an x out here in this dx thing, it's not going to be a big deal. Wait a minute. You know what I forgot? We have to square this whole thing, which leads me to wonder, did I actually even write that on my paper? I don't know. We'll see in a minute, right? All right, so I need to insert parentheses, and I messed all this up. So you don't have to retype. You can just hit INS, which stands for insert. So second delete insert changes your cursor so you can type in some parentheses. Okay, very good. And then minus, instead of a y plus 2, we'll have an x plus 2. Put an x over here at the end of it. Oh, wait a minute. I did it again, didn't I? I forgot to close the parentheses and square it. Yeah, that looks approximately right. And then there's our area. It's tiny. And then for AP reasons, we would say truncate that as 1.544 or run that final 4 up to a 5 because of the 6 that's right there. Okay, so let's go back over here. Notability, why don't you go ahead and restart for me again? Let's see, did I type it in right? I didn't even write anything down. I didn't write anything down. Okay, so anyway, it was from A to B, where our A and our B were the numbers that we stored into the calculator, and it was the quantity, the natural log of y minus, it's minus y minus 2, so I'll distribute the negative sign through there, so that's the reason why it was plus 2 dy. Oh yeah, don't forget to square this thing, right? Because the thing that is inside the integrand is essentially our area of our cross-section squared, and then the dy makes it a volume. Now, you know what we did here actually in the calculator was this. Here, let me copy this thing. Let's copy it. Let's paste it. Right? What we actually did in the calculator, though, was instead, everywhere there was a y, we put an x. Yeah. So you know what that actually did? What that actually did was this. You know what? I have a picture stored here someplace of the graph. If we solve our equation for each one of these equations for x, and then we switch the x and the y coordinate, basically what we just did is we graphed the inverses. So if I flip that across the line, y equals x, let's maybe switch to, I don't know, like this lovely green color, and then here is the natural log function, it's approximately like that. And then we have our line. Our line goes from, looks like a -2 down here and a +2. So doop and a doop right here. And let it straighten itself out. There we go. All right, so this region. Right, so our horizontal representative rectangle, that's right there, when it gets flipped across the line y equals x, becomes a vertical representative rectangle. I'll get purple again. Like, why not? Right, with a delta x, right? So here's the equation, y is equal to the natural log of x, and this is y is equal to x minus 2. Right? So essentially that's what happened whenever we put this into the calculator like that, and it gives us the exact same volume for that shape. Okay, so you don't actually have to worry about finding the inverses of each of these equations. Like if you're integrating these things by hand, you wouldn't have had to switch that to an x coordinate. We just had to do that in the calculator because it was so much easier to type in the x key than alpha y.